Okay?
Yeah, that's what I was like.
Ready?
Yes.
Very good. So the numerator is x cubed plus 4. Now the denominator. Well, let's say we don't remember how to factor this. Let me show you again. Minus 1 equals 0. Okay? I don't need to write it. It's not an equation yet. So let's just factor it. And then we'll set it equal to 0. Or I can keep it as that. It really doesn't matter. Okay, so I multiply the first coefficient by the last coefficient, meaning I have to try to find two numbers. I'm looking for two numbers whose product is -2 and whose sum is always the coefficient of the middle term, 1. That doesn't change. Now, if the leading coefficient is 1, I don't have to multiply anything, this by this. The product is this. But since the leading coefficient is not 1, I will multiply 2 by -1, and I get -2. Can I find two numbers whose product is -2 and whose sum is 1? Remember, the product is negative, so definitely one has to be positive and one has to be negative. Then the sum is 1, so the positive number is bigger in absolute value. So can I find those numbers?
So, 2 and -1.
2 and -1. I will replace the middle term using 2 and -1. So 2x squared plus 2x minus 1 equals 0. I used 2 and -1 that you gave me, and this is still x. So I didn't change the problem. I changed the presentation, the outlook. But this is more useful. Now, I have 4 terms. If you make the mistake of going back and say, okay, let me combine like terms, then we just annulled what we just did. So I can go back and combine like terms. But what do I do next moving forward?
You use group.
Grouping, very good. So I will group these two and these two. If that doesn't work, then I will group the first with the third and the second with the fourth. So I will not conclude that it's not factorable, and I know already it's factorable because I found the two numbers, so there's no discussion there. I know this is factorable, because otherwise I would not be able to find two numbers whose product is this and whose sum is this. Since I found them, I know it's factorable. Okay. Of course, you can also solve the equation using the quadratic formula. You don't have to factor if you don't want to. So anyway, I factor out 2x, and then I get x plus 1. And remember what I like to do. I cover this, and what do I have to have coming out of the other two? Otherwise, I can't continue.
X plus 1.
It has to be x plus 1 because this has to be the common factor that gets pulled out. And now I look. And I'm not just saying or making this up. This is exactly the way I do it.
So equals -1.
-1. So now I pull out x plus 1, and then in parentheses,
2x minus 1.
indeed. So then I go back and I copy it as x plus 1 and 2x minus 1. Okay, what do I have to do first? Right? But in the chart, what do I have to put first? What is my first step?
The asymptote. So
It has to be the
-1.
domain, yes, right? So negative infinity, -1, 0, what else?
1/2.
Very good, excellent. So now I'm asking myself, does any of these factors go away? No, x cubed plus 4. I can't factor that. So, and I know there is no x plus 1 factor in here, and there is no 2x minus 1 factor in there. If that was the case, if I could have simplified one of them, then I would have said it's a hole in the graph. But it's not the case. So I can already write x equals -1 and x equals 1/2. What?
Speed.
Yes. I can already write what? So if you like this chart and you use it, when you fill it up, then you know you're done. So you're not going to forget anything.
We need to write the infinity sign.
Exactly. That's my next step. However, it's not done because I have to check the sign, find the sign. Okay, so as you see, I do not put these numbers in the chart. They're up there because I'm gonna, or out there because I'm gonna use them. So this is 0.5, so 0.4 and 0.6. Okay, so I go back. Now, negative 1.1 cubed, right, but negative 1.1 cubed, will it cover, will it exceed 4 or not? It will not exceed 4, very good. So the top is positive. Can I say the same thing for all these numbers? If I put negative 0.9 to the third power, will that exceed 4? No. And the other two are positive. So I don't have to worry about this, around this, or that. So now, negative 1.1, we're going to catch the mistake in a blink. Because if what I put in here doesn't make any sense, then I know there is something wrong. Okay? Good. So negative 1.1, the sign for this. The sign for 2x minus 1 was negative 1.1. So 2 negatives. Good. The sign with negative 0.9. Negative 0.9 plus 1. Correct? Now careful. 2 times negative 0.9 is negative 1.8. With minus 1. Negative. So then the sign is negative.
So if you already determine one side's positive, can you just assume the other side's negative?
Nope. Let me tell you why. This is an option. This is an option. This is the third, and this is the fourth. You can't assume. Good. So with 0.4, this is definitely positive. With 0.6, this is definitely positive. So all I have to do is in here, right? So I know how to graph this. It's a linear function with a negative slope, with a positive slope, negative and positive. But let's plug it in. So 2 times 0.8 is 2 times 0.4 is 0.8. It will not exceed this. So this side is negative. And with 0.6, it will exceed. It's 1.2 minus 1. So this will be positive. Good. Now I need the x and y intercepts. How do I determine the x-intercept? I set y. This is a fraction. When is a fraction 0? Exactly. So x to the third plus 4 equals 0. I move 4 to the other side. You can say, wait a minute. This function or this polynomial equation has 3 solutions. I agree. However, only 2. Only one of them is real. How will I know? How will I know that this function only crosses the x-axis once, although it has degree 3, and it has to have, and I keep saying that many times, right? Degree 3, 3 solutions. Degree 4, 4 solutions. But now I have degree 3, but I claim that this function only crosses the x-axis once. How do I know? You don't. Not for the cube root. Let's think in terms of chapter 2. Forget about this for a second. How do I graph x cubed? And what do I do? How do I graph x cubed plus 4? How many times will this function cross the x-axis? Although it has 3 solutions, 2 of them are imaginary. So that's why we study those transformations, to quickly imagine. So let me just show again. As we know that this is x cubed. And now we know why it looks like this. Why it looks like this? 3 solutions that are the same, right? And now this is x cubed. But when I want to graph x cubed plus 4, I will graph this. So how many solutions and how many points will this function cross the x-axis? So that's why I take the cube root and I have no idea what that is. So I'm going to put in the calculator. So let me show you. Here it is. So one option is, what is the cube root? Oh, I didn't write it there. Sorry, it's a cube root. Okay, 3, not squared. Okay, so one option would be, in parentheses, -4, close the parenthesis, power. What power is the cube root? 1/3, very good. So in parentheses, 1 divided by 3. So that's one option. Here's the second option. Go to math, and you select 4, and you put -4. You know, me, I'm old school. I have to have parentheses everywhere. I'm sure the software takes care of that, but I don't believe anything. Okay? So then I know that the x-intercept is -1.6, 0. Okay? I'm sorry, that's what I meant, -1.6, right? So the ordered pair. So -1.6, this is -1. I have to be very careful where I put this. -1.6, 0. Final step, I need the x-intercept. I shouldn't say final, it's not final. What is the x-intercept? When x is 0, let's go back here. I prefer this form for the x-intercept. Exactly. Perfect. Very good. Can this function be symmetric if it has a vertical asymptote at -1 and a vertical asymptote at 1/2? Can it be symmetric with respect to the y-axis? Can it be symmetric with respect to the origin? No. But I have to write something about it. Okay. So I'm going to say that f of -x suddenly does not equal f of x, and it does not equal -f of x, not symmetric. Now, final step. I fill up my chart. I have the x-intercept, I have the y-intercept, I have the vertical asymptotes. They are clear. I have the infinities, but I'm missing this and this. That's the only thing I'm missing, right? Under negative infinity, infinity. However, because this is type 3, how do I determine the end behavior? I have to determine the slant asymptote. If the slant asymptote looks like this, then the end behavior is negative infinity to positive infinity. If the slant asymptote looks like this, then the end behavior is positive infinity going to negative infinity. So now I have to find the slant asymptote. Ready? So the top is x cubed, but x squared is missing, x is missing, plus 4. And I divided by 2x squared plus x minus 1. Both are in descending order. Only this one, if it has missing terms, only that one has to, I have to leave room. Now, can I use synthetic division on this division? No, because the denominator is not x minus a number or x plus a number, correct? Okay, so let's give it a shot. What degree do I have to get? 1, absolutely 1. It has to be a line. I could never get a degree other than 1. It will not have, if a degree is 4 and 2, it will not have a slant asymptote. Because when I divide degree 4 by degree 2, I don't get a line. So when I divide degree 3 by degree 2, I get a line. Perfect. So 2x squared multiplied by what is x cubed? 1/2 x, yes, 1/2 x. We go back, we distribute. 1/2 x times 2x squared, x cubed, but I have to write minus. 1/2 x times x, it's 1/2 x squared minus 1/2 x squared. 1/2 x times -1 is -1/2 x, so plus 1/2 x. Gone? I should have not written this here. It's in my way now. I'm gonna just put it like this. Okay. I bring down the next in line. I'm gonna bring it here because I put this in the way. So negative 1/2 x squared plus 1/2 x. I bring down the next in line. Final question. It must be the final question. I cannot have anything else here. Just a term with x and a free term. That's it. 2x squared times what equals negative 1/2 x squared. So this is okay. It's right here. What would I multiply 2 by to get negative 1/2? It has to be negative, because 2 times a negative number will be negative. And I have to be able to simplify and still get 1/2. 1 divided by 4. I'll simplify and I get negative 1/2. So it's minus 1/4. So negative 1/4 times 2x squared. I'm done, but I should finish the division. I'm done. This is the slant asymptote. But I still have to finish the division. I cannot just leave it in the middle because I'm not interested in the remainder anymore. Right? So negative 1/4 times 2 is negative 1/2 x squared, but plus 1/2 x squared. Negative 1/4 times x is negative 1/4 x, but plus 1/4 x. And negative 1/4 times negative 1 is positive 1/4, so negative 1/4. So 50 cents plus 25 cents is 3/4. 3/4 x. And from 4, when I subtract a quarter, I get 375, right? From 4 minus 1/4, the least common denominator is 4. This gets multiplied by 4. 16 minus 1, 15. So it's positive 15/4. How will I write the answer? I don't need to write the whole thing because this is not what I'm interested in, but since we are practicing this, let's write the correct answer. So I have x cubed plus 4 over 2x squared plus x minus 1 can be rewritten how? Yes, 1/2 x minus 1/4 and plus what? Exactly. The top is 3/4 x plus 15/4. Everything divided by? Now, here's just a thought for you. Since this will give us the end behavior, how come that this doesn't count? Can anyone explain how come that this doesn't count when x approaches infinity? For a moment, look at this function and say, I know the type. What type is it? 1, 2, or 3? 2. Where does this go at infinity? Exactly. That's why this is what counts. Because this one at infinity will go to infinity. But this one at infinity will approach 0. That's why we don't even look at it. So therefore, y equals 1/2 x minus 1/4 is the slant asymptote of this function. Since the slant asymptote it looks like this, or it looks like this, tell me which one, and then we can put the end behavior. Exactly. Negative infinity to infinity, and the slant asymptote is 1/2 x minus 1/4. Is that clear? Good. So now we're ready to graph. I don't need any of this, nothing. I only need the chart because the chart tells me what to do. The rest, everything is summarized in there. So let's discuss it before we even do anything. What is the first thing I have to graph when I graph a function with asymptotes? Right. And this function has how many asymptotes?
3.
Yes. It has 2 vertical ones at -1 and 1/2. X equals -1, x equals 1/2. And it has a slant asymptote, and I have to find points for the slant asymptote. When x is 0, y is negative 1/4. So if this is a unit, 1, negative 1/4 will be here. Now when y is 0, let's write that. 0 equals 1/2 x minus 1/4. I move 1/4 to the other side, and I multiply both sides by 2. So then x equals 1/2. Right? So I move this, multiply both sides by 2, and I get 2/4, which is 1/2. So 1/2, 0. It's right here. I have the points for the slant asymptote, and now I'm ready to graph the slant asymptote. These are not part of the graph. They cannot be solid lines. I have to write what I graphed. I graphed y equals 1/2 x minus 1/4. Okay, now I'm ready to read my chart. Ready? Okay. I do have a negative 1.60. So if this is 1 and this is 2, negative 1.6 is here. I do have a 0, negative 4. That's what happens when you don't plan ahead, like me. So negative 4, negative 1, negative 2, negative 3, negative 4 right here. And nothing else. Right? These are the only 2 points I have. Good. So I'm trying to make sense of this information. From approaching at negative infinity, from approaching the slant asymptote, the function will cross the x-axis at this point, and then it will go towards infinity on the left-hand side of the first asymptote. So here's what I presume happens, right? From approaching the slant asymptote, crossing at negative 1.60, and going to positive infinity on the left-hand side of the asymptote. Is this portion clear? Yes? Is it? One more time. From approaching the slant asymptote at negative infinity, crossing the x-axis at this point, and going up to positive infinity on the left-hand side of the first asymptote. Is that clear? Now we are in the middle. It's coming from negative infinity on the right-hand side of the asymptote, coming up to this point, 0, negative 4, and all of a sudden comes back to negative infinity. So it looks like a parabola. So again, I have to extend my vertical asymptotes. And I'm going to graph this. However, I don't believe it. I don't believe that the function turns exactly on the y-axis. I am tempted to believe that the function will do this. Or, which is not, I don't think that's the case, here, which is not the case. Almost sure. Okay? So this portion, I don't know. I can plug in numbers. I can plug in numbers on the left-hand side and see if this number is higher than negative 4. No need. Really no need here. Because we're going to address this in the next course in detail by hand. No need. Okay, final step here on the right-hand side. From approaching infinity on the right-hand side of the second asymptote, vertical asymptote, going back to infinity. That's not possible. There is no function that connects infinities, right? So it has to have a minimum. So I don't know where the minimum is, but there is no discussion that that's going to be the case. There is no way. It can be a straight line between infinity and infinity. That's not possible. So it must have a minimum somewhere. This is the function, which is x cubed. Very good example. Wonderful. Thank you for choosing this. Okay. So let's look at it with a graphing calculator, and then I like to look at it with Maple. Although we have to create two functions there. Okay, so we had x cubed plus 4. Don't forget parentheses. X cubed plus 4. Close the parenthesis. Divided by, ouchie, sorry. I always do that with this software. Close the parenthesis. And divide by x squared plus, no, it was 2x squared, right? 2x squared plus x minus 1. 2x squared plus x minus 1. Close the parenthesis. Plus x minus 1. Okay. So now I need a second function, right? What is the second function? 0.5x minus 0.25. Okay? Now, where will I graph it? Well, I know for sure that the viewing window, I shouldn't say for sure, but the viewing window should work, but it may not work for that minimum. It might not show the minimum. I don't know. I'm going to use the viewing window, the standard. I'm going to say zoom 6. Let's see what happens. Here comes from negative infinity crossing a negative 1/6. Ah, wonderful. So it's coming from negative infinity, crossing a negative 1.6, going to positive infinity. I know there is a vertical asymptote here. And as I predicted, I have not looked at this function before. It cannot turn right there. It's not in the middle. If it's in the middle exactly, I could have said, yeah. But one side is at 0.5, the other side is at -1. Unlikely that it will turn on the y-axis. And you see the maximum is here, to the left of the y-axis. And then it's coming from positive infinity, from a vertical asymptote of 0.5, it comes to a minimum, and again, of course, it has to approach the asymptote. So I'm going to determine this maximum with second and calc. So I know the maximum is between negative 0.5 for sure. I want the maximum. I have to give the calculator a portion where to look. So if this is a negative 1, I'm going to say negative 0.8, the leftmost point. And the rightmost point I can see at 0. And I don't want to guess, just give me the maximum. So the maximum is negative 3.5, not negative 4. Right? So I will put it in my chart. Negative 0.3 roughly. And negative 3.5. So this is the local max. And now I want to determine that minimum. And I definitely see it's somewhere between 1 and, let's say, 4. So second and calc, minimum between 1 and 4. Just give me the minimum. And here it is. At 2. 1.33. So 1.3. As expected, this function cannot connect. There's nothing that connects infinities. It has to come to a minimum and then go back to infinity. Very good example. Yes, it took us a while because it was not a trivial problem. So this is okay, but you know now this is the correct graph. And we determined that point too. So it appears that it's a little bit lower, something like that. Good. Any questions on this? Any questions on this? I do have one quick question for you here to work on. It's not from what we did yesterday. It's from polynomials. So. And in the meantime, I will put this function in Maple that we just graphed. See what Maple gives us.